So let's go deeper inside. We now introduce the two-level factorial design, one of the most important and widely used experimental designs for studying multiply factors and detecting interaction effects. The two-level factorial design studies multiply factors simultaneously, each at low and high level, allowing us to evaluate all combinations efficiently. It is especially useful in simulation because it can reveal interaction effects while requiring relatively few experiments. For example, for factors requires only 16 runs. Here we study two factors, passenger demand and headway, each of two levels, coded as -1 for low and +1 for high. This produces four experimental combinations, allowing us to estimate both the individual effect of each factor and their interaction on passenger waiting time. The regression model summarizes how demand, headway, and their joint effect influence the system performance. On this slide, we estimate the regression coefficients using the four simulation results. We substitute the observed waiting times, y1 to y4, into the model equations and solve for the coefficient q0, qa, qb, and qnb. Here, q0 represents the overall average waiting time, qa and qb represents the main effects of a passenger demand and headway, and qab captures the interaction between them. The final fitted model shows how changing each factor from its low level to its high level affects passenger waiting time. The following slide shows how factor effects can be computed using the sine table method. By multiplying each response by the corresponding factor sines and averaging the results, we obtain the model coefficients. The baseline waiting time is 40 minutes. Passenger demand has the strongest effect on waiting time, while headway has a smaller, moderate effect, and the interaction between them is relatively weak. Therefore, managing passenger demand is the most effective way to reduce waiting time. Here we are discussing how to quantify the importance of each factor using the allocation of a variation. The total variability of the responses is decomposed into parts explained by factor A, factor B, and their interaction. By comparing each sum of squares to the total, we obtain the percentage contribution of each factor. So, for example, if SSA divided by SST equal to 0.6, demand level explains 60% of the variability in passenger waiting time. A basic 2K factorial design uses only one run per experiment, so it cannot estimate experimental error. Because simulation outputs are affected by randomness, a single run is not reliable. The solution is replication, repeating each experiment multiple times and analyzing the average results. This creates a 2KR design and follows us to quantify variability and confidence in the estimates. The extended model therefore includes an error term representing simulation noise. When replications are used, analysis is based on the average response for each design point rather than individual runs. Each row represents one factor combination, while the listed values shows result from repeated simulations. The deviation of each run from its mean represents simulation error caused by randomness. By summing the squared errors across all runs, we obtain SSE, which quantifies within experiment variability. This allows also estimation of the standard deviation of errors and the reliability of the results. Factorial experiments allow us to quantify how strongly each factor impacting system performance. Main effects highlight the most important operational drivers, while interaction effects reveal dependencies between factors. Variance allocation further shows the relative importance of each factor in explaining performance variability. Together, those results support evidence-based decisions on which interventions will be most effective.